Good afternoon, everyone. Today, we're going to present the basic concepts of crystal structures, presented by Group 1. Our objectives are understand the basic concept of crystal structures, learn about the different types of crystal systems and lattices, understand the concept of symmetry in crystal structures, learn about the close packing in crystal structures, understand the different types of crystal defects and their impacts. Our overview, introduction, atomic arrangement, crystal systems, symmetry, crystal lattices, close packing, crystal defects, and finally, our conclusion. So, what is crystal structure? The crystal structure of a material formed by repeated arrangement of atoms, ions, or molecules dictates its physical and chemical properties like density, melting point, and optical behavior. Varieties like rhombohedral, orthorhombic, cubic, tetragonal, monoclinic, and triclinic arise from different atomic arrangements and bonding. Understanding crystal structures is crucial across geology, chemistry, and material science due to their influence on a material's characteristics. Atomic arrangement. Atomic lattices, the basic building block of a crystal structure, is the atomic lattice, where atoms are arranged in a repeating pattern. Unit cell, the smallest repeating unit of crystal lattice that, when stacked together, forms the entire crystal structure. As we can see, the blue part of the square that we can see is the unit cell.
System refers to one of the many classes of crystals, space groups, and lattices. In crystallography terms, lattice systems and crystal, the systems are associated with each other with a slight difference based on their point groups. Crystals and space groups are divided into 7 crystal systems. The crystal systems are differentiated by the relationship between the angles between the sides of the unit cell and the distance between points in the unit cell. One of the 7 different crystal systems is known as the cubic. It is the most symmetrical one out of the 7 crystal systems. All 3 angles intersect at right angles and are of equal length. Crystal shapes of a cubic system based on inner structure. The tetragonal system. 3 sides of an equal length but one angle different from 90 degrees. It consists of 3 axes. The main axis varies in length. It can either be short or long. 2 axes lie in the same plane and are of the same length. Based on the rectangular inner structure of the shapes of crystal in tetragonal include double and 8-sided pyramids, 4-sided prism, and trapezoid rounds and pyrite. Big, all sides are of different lengths and all angles are 90 degrees. It has 3 axes and is at right angles to each other. There are different lengths based on their rhombic structure. The orthorhombic system includes various crystal shapes, namely pyramids, double pyramids, rhombic pyramids, and pinacoids. Some common orthorhombic crystals include topaz, tazzanite, lowlite, zoisite, tanburite, and more. Tetragonal system, 3 equal sides with angles of 60 and 120 degrees. 4 axes, the 3 A1, A2, and A3 axes are all contained within a single plane, basal plane, and are at 120 degrees. They intersect each other at an angle of 60 degrees. The 4th axis intersects other axes at right angles. Crystal shape and hexagonal systems include double pyramids, double-sided pyramids, and 4-sided pyramids. Examples are beryl, concrinite, apatite, sugliite, and etc. The trigonal rhombohedral three equal sides and angles are not equal to 90 degrees. The angles and axes in a trigonal system are similar to hexagonal systems. At the base of a hexagonal system, there will be 6 sides. In the trigonal system, there will be 3 sides. Crystal shapes in trigonal systems include 3-sided pyramids, scalenohedral, rhombohedral, and some typical examples include ruby, quartz, calcite, agate, jasper, tiger's eye, and more. Clinic, all sides of different lengths, 2 angles are 90 degrees and 1 angle is not. Comprises 3 axes, where 2 are at right angles to each other and the third axis is inclined. All 3 axes are not of different length. Based on the inner structure, the monoclinic system includes basal, pinacoids, and prism, with inclined end faces. Some examples include diopside, petalite, kanzite, gypsum, hydonite, howlite, vivianite, and more. The triclinic system. Crystals in this system are referred to 3 axes of unequal lengths that are inclined at a non-orthogonal or non-perpendicular angles relative to each other. It is the most unsymmetrical crystal system. All 3 axes are inclined towards each other and they are of the same length. Based on the 3 inclined angles, the various forms of crystals are in the paired bases. Some standard triclinic systems include labradorite, amazonite, kyanite, rhodonite, aventurine, feldspar, and turquoise.
Symmetry. Symmetry elements such as rotation axes, planes of reflection, and inversion centers characterize the symmetry of a crystal lattice. As we can see here, the picture on the left side of the slide. And while space groups descriptions is the descriptions of the combinations of symmetry elements present in a crystal structure. As we can see in the left side of the slide again, we can see that the space group is highlighted. Crystal lattices. There are 3 crystal lattices, which are number 1, primitive lattice. It's the simplest repeating unit cell with lattice points only at the corners. As we can see on the picture, the primitive lattice has only lattice points at the corners. Number 2, body-centered lattice, which is lattice points at the corners and one in the center of the unit cell. So you can see in the picture, body-centered lattice, points at the corners, and one in the center of the unit cell. Number 3, face-centered lattice. Lattice points at the corners and one on each face of the unit cell. As we can see, the face-centered lattice are at the corners and one on each face of the unit cell. Close packing. Hexagonal close pack or HCP atoms are arranged in layers with a hexagonal arrangement and stacked in an AB sequence. As we can see on the picture on the right side. Number 2, cubic close pack or CCP, also known as face-centered cubic or FCC, that is, atoms are arranged in layers with a square arrangement and stacked in an ABC sequence, as you can see on the right side of the picture. Crystal defects. There are 3 parts of the crystal defects, which is the point defects. Point defects includes vacancies missing atoms, interstitial atoms or extra atoms, and substitutions or one atom of atom replaced by another. Number 2, Line defects are dislocations where there is a linear misalignment of atoms. Number 3, planar defects. It includes grain boundaries or region between crystals of different orientations and stacking faults or errors in the stacking sequence of atomic layer.
For the conclusion, the study of crystal structures reveals the ordered arrangement of atoms, ions, or molecules within solids, which is essential in many scientific fields. Different lattices, symmetry components, and crystal systems characterize possible structures. Point, line, and planar crystal defects introduce imperfections significantly affecting material properties. Comprehending these imperfections makes engineering materials for customized features in various applications easier. In the end, this thorough comprehension of crystal structure serves as the foundation for discoveries and advances in material science, which influences development in various sectors.